So this is problem 224 from the book. And the statement of the problem is that we have two forces, F1 and F2, acting on a screw eye. And we're told that their lines of action are at an angle of theta apart from each other, and that the magnitude of each force is the same. In other words, the magnitude of F1 is the same as the magnitude of F2. So we're just going to call it F, just for simplicity, because they're both the same value. So now the problem asks us to determine the magnitude of the resultant force. So we know from vector addition that if we add up the two vectors F1 and F2, we get a resultant force vector F sub r. But here, we are asked for the magnitude of that vector. And you know that when we're dealing with magnitudes, we can't just add them up like we do with vectors. So we want to find the magnitude of my resultant vector. And then we also want to find the angle between my resultant vector and F1. So I'm going to draw kind of what they're asking from us. That way we can have an idea of what we're looking for. So let's say that if you were to add F1 and F2, let's say that we get a resultant force more or less in this direction. This is just an approximation. I'm not really sure if it's going to be horizontal or not. It may not be. But let's say that we get a resultant force in this direction. So they're asking us for the magnitude of this resultant force. And they're also asking us for the angle between the resultant force and my force F1. So we're going to call this angle phi. We already have an angle theta, which is this angle. So we don't want to call it theta. We're just going to call this angle phi, and that will be a little bit easier for us to manage. So that's the problem statement right now. We want to find the magnitude of this vector. We want to find the angle between the vector and vector F1. Now notice that they're not giving us any numbers here. So usually when students don't see numbers, they get scared. But the procedure is actually the same. So even though they're not giving us numbers, that means we don't have to plug anything into a calculator. We can still solve the problem if we know the basics of vector addition. So when we have a problem like this, you have different ways of solving it. You can use the parallelogram law. You can use the triangle rule. Some students may even want to split it up into components. Now, I think the component approach may not be the best approach to take here, but instead, I'm going to focus on the triangle rule or the parallelogram law. So whichever method you choose, you should be able to solve the problem and get the same answer. But if you need a refresher, the parallelogram law says that we can start our two vectors from the same origin point. And then if I were to redraw this vector, but starting at the end of my second vector, and if I were to redraw my F2 at the end of F1, what's essentially I end up with a parallelogram. So this would be a vector identical to F1. This would be a vector identical to F2. So I end up with what is a parallelogram. And parallelograms help us because if you remember your geometry, a parallelogram is a shape, a polygon that has two sets of parallel sides. So these two sides, F2, F2, are not only parallel, but they have the same magnitude. Same thing with F1 and F1. So if they have the same magnitude, the parallelogram law tells us that the opposite angles in the parallelogram should be the same. So if this is theta, then that means that this one is also theta. So that's one of the cool things about the parallelogram law is that it allows us to find angles. Another thing we know is that the sum of angles in a parallelogram or any other quadrilateral is 360 degrees. So I'm just going to write down that here so you can remember it, the sum of angles in a parallelogram is 360. Okay, so make sure you keep that as a reminder so you can use this law in the exam if you have to. If the sum of angles in a parallelogram is 360 degrees, then that is actually going to help us find these two angles. Because now we know that theta plus this angle is equal to 360 degrees. But we also know that these two angles are the same. So we know that 2 theta times 2 times this angle should be equal to 360 degrees. So what does that tell us about this angle? That means that this angle is equal to 360 minus 2 theta. And that's equal to the sum of these two angles, but since they're both the same, we divide it over 2. So that means that this angle and this angle are both going to be equal to 360 over 2, that's 180, minus 2 theta over 2, that's just theta. So that's what we get from the parallelogram law. I mean, we're not getting any numbers, like I said, because we're not really plugging in or using numbers. But the parallelogram law should at least give us an idea of what the angles are. Now, why do I do this? Because I'm going to switch from the parallelogram law into what's called the triangle rule. Now, the triangle rule tells me that I can draw a triangle by starting a line at my first vector, so this would be f1, and then continuing it through my second vector, that is f2. Now, it doesn't matter which side you choose. You can start at f1, continue through f2, or you can start a path at f2 and continue through f1. The important thing is that you always continue through a full path so that your triangle can be found by closing the start of one vector to the end of the other vector. And that is the triangle rules. So if I were to draw my triangle, I'm going to draw a little bit bigger here so we can work with the angles. I would essentially have my f1 vector, my f2 vector, and my resultant force vector. So that is the triangle rule. Let me write down the names of the vectors here. We have f1, we have f2, and we have our resultant vector, fr. So in the triangle rule, now we need to figure out what angles are we given, what magnitudes are we given. So we know a couple of things. We know that f1 and f2 have the same magnitude, which means that in this triangle, f1 and f2 will have the same side lengths. We also know that the big angle in this triangle is 180 minus 5, which we got from the parallelogram law. So I'm going to write it down here, 180 minus theta, minus theta. And then we also know that the angle between fr and my force f1 was given the name phi. So we just gave it this name. You can give it any name you want. But what we know is that this angle was given the name phi, and this is one of the angles that we have to find as part of this problem. So we're slowly starting to figure out what we need to find. So we have our phi angle here, and this is our end goal. We have our resultant force, and we also need to figure out what the magnitude of this force is. And now we can find this missing angle, which we don't really know what it is, but we do know that the sum of angles in a triangle is 180 degrees. So again, I'm just going to write it down here for reference. So the sum of angles in a triangle is equal to 180 degrees. So if we know that the sum of angles in a triangle is equal to 180 degrees, then I know that phi plus 180 minus theta plus this angle should be equal to 180. That means that this angle is equal to 180 minus phi minus 180 minus theta. Okay. Don't forget to write down your parentheses. But essentially, if you were to solve this angle, we get 180 minus 180, that's 0. Then we get negative phi minus negative theta. So that's negative phi plus theta. And if I just want to write it a little bit cleaner, I can just write theta minus phi. Just flip these two around. So we have a triangle. We have a triangle with phi, an angle 180 minus theta, and an angle theta minus phi. So those are all the angles in a triangle. And now the question is, do we know what to do with them? Well, we're asked a couple of things, right? We're asked to find the magnitude of that resultant force. Now, if we are given our force magnitudes F1 and F2, and we are given the angle, the measure of the angle theta, then we should be able to find the magnitude of the resultant force by simply applying either the cosine law or the sine law, whichever you prefer. Now what I'm going to do is I'm going to first try to find the relationship between theta and phi. Because we're told that the magnitude of the forces is equal to each other. In other words, F1 has the same length as F2. So what I can do now is, like I said, I can apply the cosine or the sine law in order to find out different relationships between force magnitudes and between the angles. So I'm going to start with the sine law. I think that would be the easiest one. Do you remember the sine law? If you need a refresher, the sine law is simply states that the sine of an angle A divided by the length of the opposite side A in the triangle is equal to the sine of angle B divided by the opposite side B, and it's equal to the sine of angle C divided by its opposite side C. And that is in a triangle where A, B, and C are opposite to their respective angles. So that's the sine law. So if we look at this triangle, how can we apply the sine law? We know that F1 and F2 are the same. So let's try to apply a sine law that includes F1, F2, and its opposite angles. So I'm going to start with F1. What is the opposite angle for F1? Which of these three is the opposite angle?
Be theta minus phi.
Exactly. It's theta minus phi is the opposite angle to F1. So I can apply the sine law and say that the sine of theta minus phi divided by the magnitude of F1 is equal to, and now I'm going to use F2. What's the opposite angle for F2?
Phi.
Yep. Equal to the sine of phi over the magnitude of F2. And now I have something interesting here, because we said that F1 and F2 have exactly the same magnitude. So if F1 and F2 are the same, then essentially we can just cancel them out, right? If you multiply both sides by F1, then F1 cancels with F1, and F1 cancels with F2 because they are exactly the same. So I can cancel out from this equation my F1 and my F2, leaving me with the expression sine of theta minus phi equals sine of phi. And now, if the sine of theta minus phi is equal to sine of phi, then that means that the inside terms of the sine should be equal to each other. And if you're not sure how or why that works, think of it this way. You have an expression of sine of something equals sine of something else. Then why don't you just apply the inverse sine operation to both sides? You apply the inverse sine operation to both sides, and you'll end up with the inside of the operation, so theta minus phi, equals the inside of the operation on the other side, which is phi. And this is going to help us find a relationship of phi with respect to theta, because now I solve for phi and I get that theta equals 2 phi, or from that I can get that phi equals half of theta. So I have an angle phi. That's pretty good. I know that my angle phi is equal to half of my angle theta. And that's really good, because if I know that my angle phi is equal to half of my angle theta, then I could potentially just replace one of these two variables so that I can express everything in terms of one angle. Now I can do that, and if I were given numbers, then I would probably try to do that. But right now, our next step is to find the magnitude of the resultant force. Now, what we can do is find the magnitude of the resultant force by applying the cosine law. So I'm going to use a separate sheet of paper here. Now, if we need a review, then what the cosine law tells us is that a side C of a triangle is equal to the square root of the square of side A plus the square of side B plus twice the product of the magnitude of sides A and B times cosine of its opposite angle. And once again, that is the cosine law, but for a triangle with sides A, B, C and opposite angles A, B, and C respectively. What that means is that if I want to find one side, all I need is the opposite angle and the two other sides. So if we're given the magnitude of F1 and F2, then we should be able to have the two other sides. And we know that the opposite angle is 180 minus theta. So that means that we should know angle C. So I'm going to go ahead and solve this problem by saying that my resultant force, that's going to be the equivalent to my side C. So my resultant force is equal to the square root of the square of my two sides added up. So F1 squared plus F2 squared plus twice the magnitude of F1 times F2. Now we have times cosine of the opposite angle. And since this is my resultant force vector, my opposite angle will be 180 minus phi. So cosine of 180 minus phi. And now, since I know that F1 and F2 have the same magnitude, I can simplify this a little bit more. I can just write F. Here we have F times F. So I just write F squared. And at this point, we can do even more simplification, right? So we have an F2, so I can factor out my F2, F squared, sorry. So I get F squared, and by factoring out, I get F squared times 1 plus 1 plus 2 cosine of 180 minus theta. And why not factor it even further? So I can even factor this value even more, right? So I know that 1 plus 1 equals 2, and then I have 2, and then I have another 2, so I'll just factor out the 2 as well. So I have 2 F squared 1 plus cosine of 180 minus theta. Of course, we know that the square root of F squared is simply F. The square root of 2 is simply square root of 2. And then we end up with the square root of 1 plus cosine of 180 minus theta. Now, you could leave this exercise like this. And that would be a good enough answer. Because now that gives you an answer where as long as you have the magnitude of F and the value of theta, you can find the resultant force without having to do any other operations. So you can leave it this way, or if you would like, you can also try to express it a little bit differently, right? I think I did something wrong in this cosine law. Let me double check the cosine law, because I'm looking, I have a squared plus b squared. This should be minus 2ab cosine c. So I'm gonna write this here, minus. Can somebody double check the cosine law and let me know if it's minus? I think it is minus.
Yeah, it is minus.
There we go. Minus, minus, and minus. There we go. So now I can leave my answer in this way. Or I could try to express it, I could try to simplify it even further. So you can use any trigonometric rule. So from trigonometry, you know that the cosine of 180 minus theta is simply equal to negative the cosine of theta. If you don't know where that comes from, then that's all right, because you have, let's say we have our XY plane in our unit circle, and let's say we have an angle theta. So we have our angle theta. I'm going to try to draw my unit circle here. We have my angle theta, and this length is simply the cosine of theta, just this length. But now, if I'm saying the cosine of 180 minus theta, that is going at 180 degrees, that's all the way to the other side. And when I say minus theta, that means that I'm moving clockwise in the direction, at a direction of theta. So I get that this angle is also theta. So if this angle is 180 minus theta, then this angle is theta. Now what that means is that this length will also be cosine of theta. However, if we're setting our problem from the origin, we have that positive is to the right, negative is to the left. So that means that this value will be the negative of this value. In other words, the cosine of this angle is actually the negative of the cosine of this angle, and that's what we get here. The cosine of 180 minus theta is equal to negative cosine of theta. But again, you don't have to apply that. But if you do want to, then we can simplify our equation even further. We get that my resultant force is equal to the magnitude of my force times root 2 times 1 minus negative cosine of theta. And finally, my end result is force root 2 times 1 plus cosine of theta, and take the square root of that. And that's how you solve this problem. It's a bit of a long problem, and I think part of why students get scared is because it doesn't have any numbers. But notice that even if it did have numbers, you would basically solve this problem the same way. You would just have inputted a number where I now have variables. But that's 224. I think it's a good problem to solve. So I'm kind of glad that students mentioned this problem as a troublesome problem for the homework. So are there any questions with this problem?
So when I solved this problem originally, I knew since F1 was equal to F2, then I kind of made the assumption that FR, since they're the same force, that the angle phi would just be half of angle theta.
Yeah, that is
I kind of made that assumption
right
from the beginning without doing all the math.
No, that is absolutely right. So I think part of the reason why I'd like for you to see, not necessarily do, but see all the math is because you may run into a case where F1 and F2 are not the same. But you're completely right here. If F1 and F2 have the same magnitude, right, then you know that FR will run at the same distance from each angle, right? That means that we're going to have what's essentially a phi here, a phi here. And both of these combined is equal to theta. So it's a good assumption to make if both magnitudes are the same. And if you see a test and you see that two vector magnitudes are the same and they're acting in different directions, then you can tell, right, that the resultant force will run in the direction right in between those two force vectors. So yeah, thanks, Tyler. Are there any other questions? All right, so if there are no questions, then I think we're gonna stop problem 224 here and focus on other problems.